Part 7 of the General License Class Upgrade given by the Hearst Amateur Radio Club in Texas in October of 2019. This question pool lasts from 2019 until 2023. So if you're a technician and you're wanting to upgrade to General, this class goes through the W5YI book, which I'll post a link to below. You can pick up the book, follow along with the class. Be sure and check the playlist here. Start at number 1, go through, watch them all. Tell me what you think in the comments below, and good luck on your exam.
Shut up and sit down.
Welcome back. This is session 3, the third and final session of the general class license training. This evening we'll be talking about some more about components, antennas, and safety, and a few other things as well. Have any questions from the previous class? Good. We'll go on. Talk about capacitors. We're going to talk about electrolytic capacitors before. We talked about capacitors in general. We're going to talk about the electrolytic. The electrolytic is built like a jelly roll. It has interleaving layers of foil, and the foil's rolled up, and in between the foil it has a tissue that has the dielectric. It's impregnated tissue that insulates those. So you put your positive and negative together, you roll it up like a jelly roll, and you either put it in a big can to be like, you'd see these, for example, in power supplies. Very large capacitors are about the size of a soup can or larger. Also you see them in computers. Our smaller ones with radio leads are axial leads that you would find in a radio. And they're polarized. Unlike most other capacitors, which it doesn't make any difference which way you hook them up, which lead goes to positive and which lead goes to negative, these are polarized. So you have to make note of the fact that you hook the negative to the negative and the positive to the positive. And when you do that, when voltage is applied, it causes this tissue in here to become a dielectric, to become an insulator, essentially. It insulates this. If you hook them up backwards, they blow up. Here's a dielectric capacitor here. This is a small one. If you take that apart, you can unroll it. There'll be several layers of foil. One's hooked to the negative lead, the other's hooked to the positive lead. The advantage of using these is the fact that you've got a lot of capacitance in a very small size. A conventional capacitor, like that disc capacitor that's on there that has a insulator in the middle and a plate on either side of the dielectric, would be huge. Might be the size of a pie plate or larger. You hook them up wrong, the dielectric rail will start to cook, it'll short circuit, and I can tell you they'll blow up. I built a power supply one time in a plastic case with a metal lid on the top of it, and I went to test it to try it out, and I put the metal lid on the top of it, and I hooked it up, and all of a sudden I heard this hiss and this bang, and the metal lid jumped about that high off the top. It sounded like a shotgun shell went off, and there was nothing left of that capacitor except the two leads that I had hooked up incorrectly. I had hooked up backwards. Also on that thing we're passing around, you'll see ceramic disc capacitors. Their advantage, they essentially have a circular dielectric piece in the middle, foil or a conductive material on either side covered with an insulator on the outside and one lead to either side. Their advantage, they're low cost. They're not polarized. You don't have to worry about whether you hook them up correctly in the circuit. The problem is they're not very stable with temperature. And they have a wide tolerance on the value. So the tolerance, even though it's marked, may vary by 10 or 20%. That's okay. If your circuit can accommodate that, that's okay. It's not a problem. Polyester capacitors essentially are built pretty much the same way with different materials. They cost more. Now, it's all, when I talk about cost, maybe these are a nickel, maybe these are a dime. It's not that much difference. They're higher cost, they have a lot better temperature stability, and they have a lot tighter tolerance. But you'll see a lot of these in radios. You know, $3 or $4 in a radio makes a big difference in the selling price. If you can get by with these, it doesn't mean they're substandard. It just means you don't need that kind of tolerance. You don't need that kind of temperature stability. That's when you use a ceramic. You use a polyester if you needed something with closer tolerance on the value and better temperature stability. Capacitance is measured in farads. You probably remember that from your technician. Capacitors is measured in farads. Capacitors. We talked about one more door. We talked about inductors last time. And we said that inductors had reactance, which is the opposition to AC current flow. It's called inductive reactance. Capacitors also have a opposition to AC current in a capacitor, and it's called capacitive reactance. The opposite, they behave the opposite of inductors when it comes to frequency. Reactance in a capacitor increases as frequency decreases. As the frequency goes down, the capacitive reactance increases. Where in an inductor, as the frequency went up, capacitive reactance decreases. So these behave just the opposite. High frequency, capacitive reactance decreases as frequency increases. Now, the two are opposed, inductors and reactors are opposed to one another. If you remember in the previous class, we talked about an oscillator, and you saw that we had an inductor and a reactor connected together, an inductor and a capacitor connected together with each other, and they took advantage of the fact that one was decreasing while the other was increasing. So typically capacitors and inductors a lot of times in circuits, our RF circuits may be used in conjunction with each other for oscillators and filters and things of that sort. Just as you might expect, since it's the opposite, if you remember, inductors in series behaved like resistors in series in that the fact that they added up. Capacitors in series are the opposite. Capacitors in series are like inductors and resistors in parallel. Capacitors in series, the total capacitance is the sum of the reciprocals divided into one, or the reciprocal of the sum of the reciprocals. For capacitors in series, total capacitance is always smaller than the value of any single capacitor or the value of the smallest capacitor. So when combining them in capacitors, they behave the opposite of resistors and inductors. Where you put them in parallel, then they're additive. So the total of capacitance for this circuit would be, the C total is C1 plus C2 plus C3, and however many. So for capacitance in series, the total capacitance is the sum of the individual capacitors. It's always larger than the value of any single capacitor. So if you had a fixed capacitor in a circuit and you found out you didn't have enough capacitance, what would you do? One or two things. You could put a larger capacitor in the circuit, or you could put another capacitor in parallel with it. Putting two capacitors in parallel increases the capacitance. I think you might find that on your exam, maybe, if you're lucky enough to draw that question. One of the other devices we're looking at is transistors. Transistors are semiconductors. Transistors are used to amplify and switch. That's one of their primary goals, is to amplify and switch. It's composed of what's called a semiconductor material. The semiconductor material is pretty much what it says. It's not quite a conductor and not quite an insulator. It's a semiconductor. And we'll show how you can use that in just a little bit. You might find small signal transistors are going to be small, tiny little ones. I don't know if we have one on that little board that we're passing around or not. And you also have power transistors. Those are larger transistors. Those usually have the ability to mount them on a metal heat sink. They use power transistors. They'll generate a lot of heat as they pass power. And normally you would mount them either to a metal chassis or you'd mount them on a specialized heat sink. And they would reduce the heat. It would carry the heat away from the transistor. We'll look at bipolar transistors. This is the kind of simplest kind of transistor. There's two kinds that we usually use, that we normally see. These schematic symbols look like this. They're positive, a PNP transistor or an NPN transistor. And this is the symbol for the base, this is the symbol for the emitter, and this is the symbol for the collector. The easy to way acronym to remember the difference between PNP and NPN is that arrow. If the arrow's not pointing in, it's an NPN, not pointing in. The base, remember we talked about the vacuum tube, we talked about a grid and how that grid was like a valve, how that grid controlled the current going through the capacitor, the vacuum tube. It also, the base is the equivalent. So if you can you have the potential of a large current that's trying to flow through this material right here, which is a semiconductor. Sometimes it's going to conduct, sometimes it won't. It depends upon what you do with the base. It depends upon the signal or the voltage that you put on the base. So I can put on the base, I can put a small signal on my base, small alternating signal on my base, and it will control what's coming through the emitter to collector junction, and it'll create a large signal coming out. So it works pretty much the same. You've got a lot of power going in, and you've got the base operating like a water valve, turning off and on, and it will amplify. I can also turn this completely, no signal there at all, nothing will go through. Put a voltage on there, then it'll go through. I can use it as a switch. I can put either an on or off, a 1 or a 0 on there, a binary signal on there, and I can use this to turn it off and on. I can turn the transistor off and on, so I can use it as a switch, or I can use it as an amplifier. We'll talk about transformers. We'll talk about transformers. Transformers are a device that we can use to increase or decrease AC circuit, AC voltage. Where you put the AC voltage in is called the primary. Where you take the altered AC voltage out is called the secondary. How much? Depends on the ratio of the number of turns between the primary and the secondary. They're wound around an iron core. Put the primary voltage on this iron core, it puts magnetic flux into the transformer core, and you pick it back off with the secondary. So you induce a voltage into the core, and you detect that voltage and pick it back off in the secondary. If I have the ratio of the two of them determines the amount of voltage coming out with respect to, on the secondary, with respect to the AC voltage going in. This is a typical power transformer. Black's the primary. You can kind of see the windings, the insulation in between them, and you can see that metal core that we're showing right there. The transformer. Yeah.
When I hear guys talking on the radio about their primaries going bad and things, they're talking about something different though, right?
Primaries and what?
That's a good question. That's what I've been wondering. I've been hearing some of the guys talking just on repeaters here in the county, talking about the primaries went out on my this or that, or I've heard it mentioned a number of times, but I never knew.
Could be. Could be. Yeah, without knowing the context, it's hard telling whether they're using the word correctly or not.
I hate to ask, but how do you describe the primary source again? What is it?
That's where you put the voltage in.
Okay.
The voltage. Now, this could be AC. We talk about AC, we're talking about an alternating current. And you think about AC, you think about it coming out of the wall socket. And that's the one that you have there is one that comes out of the wall socket. It could also be audio, which is AC. You could transform audio. You could transform one level of audio to a different level of audio, or one impedance of audio. You could have 100 ohms impedance coming in, and you need an 8 ohm speaker. You could transform that same thing, an audio AC, with an audio transformer. Looks just the same, And you could say you want 8 ohms coming out. Well, you'd have the ratio between the 108, that would be the turns ratio between the primary and the secondary. So the primary is wherever you put the alternating current in. And I emphasize alternating current because it doesn't work with DC. DC sees it as a short. If you measure that primary with an ohm meter, you're going to find that that primary has a very low resistance. It's going to have a resistance because of the turns of wire, and you're going to find, so it's going to have a very low resistance. So it's looking like pretty much like a coil or almost a short. So if you try to put DC in here, it's not going to work. There's going to be no magnetic field. No alternating magnetic field. No mutual inductance is what causes those two to join together. And that's the core. This is a transformer. This is a primary. This is a secondary. And that's the iron core that you see here on that schematic. So we look at this. Let's say we have 100 ratio. We'll give you an example. Ratio of the transformer. We've got 120 volts going into the primary. And it has 2,250 turns. You have 500 turns coming out. Okay, the ratio of the secondary to the primary is 500 divided by 2250 equals 0.222. 120 volts times 0.222, or 0.222%, is 26.7 volts. If you change that to 1,000, that secondary would change. It'd be 1,000. It'd be a different value though. So that's how you can figure out with that ratio. Or if you knew what you wanted and you knew how many turns, you could figure out how many turns you need to put on the output. But secondary over primary gives you the ratio. You can step up or step down. Your primary could be 110 volts and you want 220 out. Then you'd have more on the output than you had on the input. Well, it's just a game that you play, the math, with the difference between the primary and the secondary. Same thing with impedance. Impedance is measured in ohms. 100 turns on your primary, 1,000 turns on your primary, 500 turns on your secondary. That's the ratio between the windings, is 500 over 100. 100 ohm impedance going in. That ratio is a half, so if you've got 100 ohms impedance going in, 0.5 times 100, or half of 100, is 50 ohms impedance. You can also change impedance. Change anything that alternates, any kind of thing, any alternating current, any current that alternates back and forth. RF energy, you can change RF energy if you want. That would be an RF transformer. Sometimes they call them balanced, sometimes they call them unins, depending on how they're used. If you had a 50 ohm, had an antenna that had a characteristic impedance of 100 ohms and you wanted to run a 50 ohm coax into it, your radio needed 50 ohms, you'd put an RF transformer in there with a 2-to-1 ratio between the secondary and the primary. They're all transformers. They all have cores in them. Sometimes the core is air, but majority of the time they use some sort of iron or metallic core to help concentrate the field. Questions on transformers? I just mentioned the word impedance. What is impedance? We talked about resistance, we talked about reactance, and we talked about impedance, and that also is measured in ohms. Resistance is simple. Resistance is pretty much constant, regardless of the frequency. Impedance varies with frequency. As we saw with inductors and capacitors, reactance varies with frequency, but it's measured in ohms. Now you may have an antenna or some kind of RF component that's made out of wire, may have a coil. It will have resistance in the wire and reactance due to the fact that it's a coil, inductive reactance. So it has both. Impedance also changes with frequency. And when you're looking at antennas, you're looking at the output of the radio, you're looking at a complex circuit there. Even what looks like a simple antenna is still complex. It has capacitance, resistive, and inductive components in it, even though you can't always see them. So it's important for good power transfer to make sure that the impedance of your source, for example, your transmitter, and the impedance of the load, which may be your antenna or something else like that, are the same. What, 50 ohms throughout, or however many ohms. If your radio uses 100 ohms and you want 100 ohms all the way through. But most transceivers and most receivers like 50 ohms. That's kind of the standard that they've settled on. So matching the source impedance and the load impedance results in the maximum amount of power transfer. Let's do a quick review. Questions at this point? Let's kind of review the stuff we talked about. Impedance, that's the opposition of the flow of current in an AC circuit. It's measured in ohms. It varies with frequency. It consists of resistance and reactance. Impedance matching is important so that a source can deliver maximum power to the load. It's complex. Impedance is complex. Capacitive reactance is the opposition to current flow in an AC and a capacitor. It's also measured in ohms. As the applied frequency increases, the capacitive reactance decreases. Capacitors in parallel add up, just like resistors. The total value is always will be larger than the value of any of the individual resistors. To increase the value of a capacitor, you can add another capacitor in parallel. The total value of capacitors in series is a reciprocal of the sum of the reciprocal of the individual capacitors. The total value is always smaller than the value of any of the individual resistors. I'm sorry, they should say capacitors. Wrong word, they should say capacitor. Electrolytic capacitors, their advantage is they have a high capacitance for a given size, but they're polarized, remember. Got positive and negative leads on them. And they're always marked, which one's a positive and which one's a negative. Incorrect polarity connection can cause destruction of the dielectric layer or short circuit, overheating and explosion. Ceramic disc capacitors, they have the advantage of low cost, although they're not very stable with temperature, and they have a wide value tolerance. The component symbols we looked at were the bipolar transistor. We looked at that the other day, the field effect transistor, when we talked about vacuum tubes. And we looked at solid core transformer. If they ask you on the exam what that is, that's a transformer. Transformer consists of two or more coils of wire. They're wound around a metallic core. The coils are coupled together through mutual inductance, through the magnetic flux that flows through that core. You can use them for transformation of voltage. You can also use them for transformation of impedance. The ratio of turns of one coil to another determines the value of transformation. You have a primary winding. That's where you put the signal in, where you put the voltage in, the AC in. And the secondary, that's where you tap it off. That's where you take it out. The transformed ratio out. Questions?